Hello friends and welcome to the third part of video tutorial series on plasma physics via computer simulation. In last part we have seen the motion of charged particle in uniform magnetic and electric field, and we have also covered E cross B drift. In this third part I am going to introduce you two new drift, Grad-B drift and curvature drift, and we will see magnetic mirror, a similar concept in this part. So let's start now. This is our fourth topic, uh, which is non-uniform magnetic field. So all this drift means these two drifts are due to the non-uniform magnetic field. We don't have to apply electric field to have grad B or curvature drift. So let's see how. Let's first discuss Grad-B drift. Okay. Now, to understand this, it is very important to learn what is grad. What does it mean, right? So let's consider a very simple case. As you can see here in this equation, we have Bz, means magnetic field in z direction. As you can see here in this picture, all these orange vectors are magnetic field, Bz vectors, right? The equation of this Bz field is such that it has some constant component and some gradient component. This B0 is constant, let us say 1 for simplicity, right? And plus some grade part. This is our simply y, and this is our gradient del bz by del y. Okay, means change in magnetic magnetic field in y direction. Let's say it has a value of 1. So to understand it, focus on this image. At origin we have some value, it is constant, right? If we put y is equal to 0 here, then bz is equal to b0. So we have a constant value at origin, but as we move along the y direction, what we find is the value of bz increases. Okay, so this is what happened. See this table. Plug y is equal to 0 in this equation. What we will have is bz equal to 1. Then plug y is equal to 1. Then what we will have is bz is equal to 2. And if we similarly put other values like y is equal to 2, then we will have bz is equal to 3. So this is how grade works, right? And we want to study the dynamics of our charged particle. What will happen if we introduce our charged particle in such scenario? Let's understand it via simulation. So here I have designed one example. So it says, let's consider a scenario depicted in the picture. As you can see here, this is our charged particle. These are the magnetic field vectors in z direction, and our grad direction is in y. Okay, as you can see here. In previous equation, b0 is equal to 3 and the value of gradient is 2. Means in this equation, b0 is equal to 3. Okay, this b0 is 3 and this gradient is 2. Simulate these inputs and draw the conclusion. So let's jump to our coding stuff. Yes. So these are the 4 Python files. I'm sorry, 3 Python files and 1 txt file, which will help us to understand the physics, right? So as I told in my previous video, this we want to study one particle. That's why I am putting n is equal to 1, t max is equal to 9, means maximum simulation time, dt is equal to 10 raised to minus 3, means the accuracy in our numerical method in Boris algorithm. This is initial.py. Okay, and I have activated inputs for Grad-B drift. I have uploaded this code on my GitHub account, so don't worry about this thing. So initially our particle is at 0 0 minus 4 means minus 4 in z direction. Okay, the velocity components are 1 0 1, x component is 1, y component is 0, and z component is 1. And this is simply our mass and charge. Okay, for simplicity I have taken them as 1. This is our main .py. Must notice that I have activated Grad-B portion, which is our case 2. So in code you can uncomment this section. See that this is our constant b0, it is 3 as I said, and this is 2, means value of grad is 2. So this much change I have done in this code, and other things, if you followed my series, this is our Boris algorithm which will help to find the trajectory. We have discussed this, so we will jump to the plotting stuff. Okay, and in this part we will animate our result. This plot data.py will help us to animate our result. Now one thing I must mention, that as we are not applying any electric field, okay, so what I have done is I have put the potential energy due to electric field is equal to 0 and commented this portion, okay, this portion of code. Okay, must remember that if you apply any kind of electric field, then change the potential energy here only, because electric field give a rise to a potential energy, so you must make changes here. But we don't have to worry about it now because we are dealing with magnetic field only, so it is 0. Okay, so let's run this. Wait a second. Yes, here's my terminal. So first we will run initial.py, which will initialize our parameter. Then we will run our main.py file, which will find the data points. Okay, and then finally we will plot our results. Let's see what we are getting. Okay, so it may take some time, but yes. So guys, as you can see here, our charged particle is kind of tracing a tilted helix. And yes, this is our energy profile. As you can see here, as expected, all three energies, kinetic energy, potential energy, and total energy of system is remaining constant. Okay, this was just to check that we are doing all things same. But here at this viewpoint, if you see, it is a complete helix, but with some tilt, right? So why we are getting this kind of a result, guys? Okay, see this kind of a result we are getting, and if you notice carefully, this tilt is in negative x direction. Okay, so let's understand this graph. Let me close other windows so that you can see. Yes, we are on our presentation and ready for the discussion. Okay, so this is our graph. From this graph we can see that energy remained constant. So this much we know, that this means that even in the case of gradient, total energy is remaining constant. Okay, now due to x and z component of velocity, positive charge is tracing a helix. This is what we have seen in previous videos as well. If we have a x and z component, then we will have a kind of a helix, right? The only difference here is we have some shift. As you can see here, this is our tilt, and after t time we have this much shift from the original axis. By the way, this red line is average line. Okay, so this much shift we have. Now can we explain this phenomena with our knowledge of Lorentz force equation? The answer is yes, we can definitely explain it, and here is the explanation. The reason for Grad-B drift, so this is the Grad-B drift. This shift is called Grad-B. Okay, the reason is grad drift, and a magnetic field with some gradient give a rise to such drifts. The simple expression of drift is given by, this is obviously for our simple case. For our simple case, the equation for Grad-B drift is given by this equation. This velocity is our drift, right? Now for this value you must notice that we have negative sign and x direction. So this negative x direction is giving rise to our tilt, right? This is the reason why we are getting tilted helix in negative x direction. Now how I derived this thing, you must refer for mathematics behind it, you must refer plasma introduction to plasma physics by F.F. Chen. In this book F.F. Chen has nicely explained how you can derive this equation with the help of Lorentz force equation. But if we want to generalize this result, right, we don't want to constrain ourselves to a particular case. If we have a general grade, for example this one, in any direction, then grade B in any direction, then what we will have? In that case we will have this kind of a drift. Okay, so B cross grade B will give us a direction of this drift velocity. Okay, now comes the very complicated curvature drift. Now why it is complicated? Because mathematics is very complex and it is difficult to understand as well. Okay, but it is one of the most important topology of magnetic field. I will tell you why it is so important. To understand it, consider the component of let me show you. Consider a velocity component of parallel. Okay, so this is our charge particle. For example, let us assume that we have a curved magnetic field like this. Okay, curved magnetic field. So when we introduce any charge particle in this kind of an environment, what will happen is it will obviously have some kind of a velocity. Then with respect to this curvature, it will have a perpendicular component and it will have a parallel component. Okay, so we will focus on this parallel component of velocity, guys. Okay, because this component give a rise to a centrifugal force. Okay, and this is what we can write, mv parallel square divided by rc, and this is our radial vector which is pointing outward, right? Here I must mention that there is no radial magnetic field. That's why I have written Br is equal to 0 and we have pure beta field. Now when we do calculation with this centrifugal force, okay, what we find is we have two kinds of drifts, right? One is curvature drift. This Vr is the curvature drift, okay, and this V grade B is our grade B drift which we have seen here. Okay, Yes, here this mixture we get as a result. So in this curvature drift, we find not only a curvature drift but grade B as well. Okay, and the proof of it is this parallel component and perpendicular component. The presence of this perpendicular component suggests the grade B. Okay, so that's why it is very complicated, guys, and understand it. Okay, so we will now jump on our code to understand this result. Let me change the value of tmax to 20. Okay, and save it in initial.py. Let me comment this portion. Okay, so yes, and uncomment this thing. Okay, yes. So here I am putting my particle on positive x-axis and y and z components are 0. The velocity vector Vx and Vy are 1 and Vz is 0, right? And M and Q, mass and charge, are 1. Okay, and let me save it again. This is our main.py. In this part, I will comment our previous example. Okay, so done, and uncomment this part. Constant b theta field means constant curvature. Okay, so this is how you can write. Okay, so this is our bx which is dependent on b theta. This b theta is 3. Okay, uh, okay, this b theta into sine theta and b theta into cos theta, this will be our y. Okay, so this is how you can introduce constant b theta field. Okay, and as our code can understand only bx and by field, that's why we are converting our b theta field into bx and by. Okay, so that's a normal thing. This is the normal conversion. So okay, we are not changing anything in our plot data.py file, and let's again run. And as I told you earlier, to run this code, first run initial.py, then we will run our main.py. As you can see here, I am running now main.py, and to plot our result, I will run plot data.py, right? Okay, so it will plot now. See guys, it is a kind of a tracing something. So let me change the camera view. So it is tracing a kind of a circle, right? Looks like a star. But good news is our energy is remaining constant. Means we haven't introduced any potential energy, so we don't expect any change in potential energy. Okay, in this side, it is tracing some kind of a star, right? And from this camera point of view, okay, our energy conservation plot is ready. We close it. So from this viewpoint, you can see guys that we have some shift, right? Notice that this blue dot is our initial data point, okay, and this vector is our final point. So there is some what we can say shift in z direction. In previous case, it was shift in negative x direction. In this case, we have a kind of a circle, and shift is in z direction. Let's discuss this thing to understand it better. Let me close this thing. Let me close the terminal as well, and this files as well, because I don't need it right now. Yes. So this red line is the average line, guys. this is from the top view, and this is some XY kind of view. Okay, so here this average red line has kind of a shift. Okay, so why we are getting such kind of a shift? This is due to the curvature drift, guys. Note that how this thing is working. Okay, this RC is in a radial direction. Okay, means which RC I'm talking about? This RC. Okay, this RC is in radial direction, and this B, okay, and B is in angular direction. So this kind of a scenario we will have. Okay, this is our radial direction and this is our angular direction. So we are doing cross product of these two, then what we will have? We will have a resulting vector in z direction. So that is the reason why we have a shift in z direction. So this was very important. You must read about this in FFchain as well. Okay, but this is a kind of a easy visualization, right? So this kind of a shift we will have. This is the curvature drift. Now I told you this drift is very important, and here is the reason. In tokamak systems, we have curved magnetic field, right? So say for example, here this is Aditya U tokamak, and this is SST1 tokamak. So in this type of tokamak devices, we use curved magnetic field to confine our plasma. Now you may ask that how can we confine our plasma as we are getting this kind of a thing. Let me okay, so how can we confine our plasma? Because there is no way, if we put positive charge, then due to the curvature drift it will hit the ceiling of this tokamak, and if we put negative charge, then it will hit the bottom of this tokamak. Then how scientists are using this curvature drift to confine our plasma? Okay, so interesting, isn't it? We are getting drift, but uh, people are using this concept to confine plasma. But clearly from this exercise we can see that we cannot confine a charged particle with this method. So I will not give a direct answer to this problem. You later Google search about it, but I will surely give you some hint. There is a thing called PF coil. Okay, uh, poloidal coil. This poloidal coils will help you to understand this concept. Okay, and you may think that how I made this kind of plots. So for that I have used my CAE code. I haven't discussed about this CAE code before, right? So with the help of this CAE code you can generate this kind of electromagnetic system. This CAE code will help you to generate to help you to design kind of a tokamak device, and it will also help you to calculate magnetic profile. I will put a link of to this code in the description. If you want to know more about this, follow this ResearchGate link. Okay, and if you want to install this or say if you want to use this CE code, you must install this Python libraries, then you will be able to use this code. So let's stop guys now. Okay, we will discuss magnetic mirror in next part of this video tutorial series. So okay guys, bye now. See you guys in the next video. Bye.